Very good morning. Today we are going to see about hydroelectric plant models and as well as the coordination between the hydro and thermal generating units. Okay, how the hydro and thermal generator unit is being coordinated and how we are scheduling, how optimally we are going to schedule these two generating units. So as we have seen in the earlier classes like hydroelectric plant models, so this is okay layout of the hydro plant. So if you see like this is the reservoir, in the reservoir, so the dam is being this wall is being constructed. Inside this, you will be having the penstock. Okay, penstock. So this penstock only will be carries the water to the turbine. That is to the turbine. This via this penstock only it is hitting the turbine, and it is being coupled with the generator. And this is the draft tube. Okay, draft tube. So the after hitting the water hitting the turbine, that water will go via this draft tube. So in like if you see like pumped storage plant via this draft tube only, what we are doing is the same generator doing the motoring action. Okay, here it is generating the power, and in the pumped hydro storage plant, the same draft tube is here. The water is coming over here. So instead of generating action, we are doing motoring action, and we are pumping the water from this stage, that is lower stage to the upper stage of the dam. Okay, we are storing the water. Okay, this is the net gross head of the dam. This four-way, this trash racks and intake. Okay, this already we have seen in the earlier classes, so we no need to go on with the detail to this like hydropower plant components. So you already very well know, you have already studied. So next, if you are going for hydrothermal scheduling, okay, hydrothermal scheduling, there are scheduling problems. There are many types of scheduling problems. In this one such important type is hydrothermal scheduling. So what we are doing is to meet out the demand. So what we have seen as of now is only thermal scheduling, a thermal generating unit scheduling. I think we have solved many problems in that thing. So if you know the scheduling of the most complex plant, that is thermal scheduling, and you can easily schedule rest all other generating units like hydro, then like renewable energy resources. So whatever the plant you'll be given, you can easily schedule. But why? Because the complex thermal generating units itself we have seen. Then rest all others are very simpler than this, not involved this much operations. Okay, if you see like hydro, then another renewable and all, not like many operations are there in the thermal. So with this, we can easily solve whatever the schedules that is being given to you. You can easily solve rest all other generating units. I hope so. Next, if you see like this hydro, the thermal, like hydro and thermal scheduling units. So why we are preferring this kind of hydro and thermal? Okay, so as I earlier said, like you should not only satisfy the load only with the thermal, whatever we have seen earlier. No, only with the thermal you can't able to satisfy the demand. Okay, so in that scenario, you can also combine with the hydro also. Why? Because why we are combining this hydro now? One of the cheapest mode of power generation is hydro. Okay, no cost, resources zero cost. Whereas in a steam power plant, the resources like coal or this coal you need to pay. Okay, the cost involved is very more. Like as I said, like 12 rupees or 18 rupees up to 20 rupees also. Sometimes it may go per unit. I'm telling about per unit cost. for generating 1 unit of power. Then if you see like hydro, it is only zero cost. Only the thing is that the maintenance, sometimes maintenance you need to pay, and the salaries to the employees, wages to the employees you need to crew you need to pay. So who are all the crew that is being involved? So that crew you need to pay for the salaries. Next, the maintenance you need to pay. So, and also the employees, the crew involved in the hydro power station will be very, very minimum. With like if you take like one hydro station, like 10 employees or maximum 15 to 20 employees might be there. Whereas if you take like a steam power station, minimum 300 people are required to the maximum of 500, and depends on the size of the thermal power plant. If it is generating capacity is more, then you need somewhat more, but minimum you need 300 employees for running, say for example, 1,000 megawatt of power plant. But if you this is the comparison, and also cost. The cost involved in the hydro is very less when compared to the steam. So why we are combining? Why we are coordinating? Okay, why we are coordinating these two in the sense. So if we coordinate only the cost of ultimately the demand also will be beat out, and also the main thing is that the cost involved in the power generation also will be reduced, and also while dispatching. The consumers also will enjoy with the least cost. Otherwise, if you scheduling only with the thermal power station for 24 hours, say for example, in a day for 24 hours we are scheduling the same power, then 24 hours means the steam power has to generate the whole 24 hours. Then the cost involved in the particular steam generation also will goes high. Will goes up to very high cost. Instead of paying per unit cost as a 5 rupees, we will pay like 20 rupees, 30 rupees. If it is only being generated with the steam power unit. So in that scenario, we are going for generation use. Yeah. So what we are doing is, here we are coordinating the hydro and steam to meet out the demand. That is PL. PL is the load or demand. So to meet out the PL load, we need to schedule this two. We are coordinating this two generating station, and we are meeting out the load. Let the power generated from the hydro as P here suffix H. P suffix capital H is the power that is being generated from the hydro generating station. And here, if you see the power generated from the steam generating unit is PS, P suffix S. Okay, so here it is discharge. Q is nothing but discharge of the water. So how much the water is being discharged in the penstock, that is directly proportional to the power is being generated. Okay, the discharge, say for example, the minimum 100 megawatt if you want to, 100 megawatt, 200 megawatt if you want to generate. So minimum discharge and speed is required is, and the speed is required is, say 120 kilometer per hour. Okay, if we hits 120 kilometer to the maximum of 150 kilometer per hour. Okay, it might be depends on the amount of power is being generated. So if you based on that, discharge also should be there. Okay, if that discharge only if it comes, that is called Q. Okay, Q. So here we already seen that this is the fuel cost, F. Okay, F is nothing but fuel cost. Similarly, Q for hydro, that is the discharge. So whatever the amount of discharge, then the power generation also will be increased. Okay, so this is the hydro generator, this is the steam generators. So the power generated from the hydro is PH, and the power generated from the steam generating unit is PS, and it is being given to the load, common bus, and that bus is connected to the load or demand. Okay, it is being satisfied with the common load PL. Okay, this is the 2-unit hydrothermal system. So only one generating unit is there for hydro, and this is also one steam generating unit is there. It is being supplied, and the power is being supplied to meet out the load. Okay, so let the we have two sources of electrical energy to supply the load. So one is hydro and another one is steam. The hydro power plant can supply the load, okay, supply the load by himself for a limited time. So here what we are doing is how much maximum hours if we are utilizing with the hydro, then automatically the cost involved is also will be reduced. Okay, so our ultimate aim, say for example, if you are given with this two, so if you utilize more with the less costliest generator, then automatically the total cost is being involved in that particular say for example 24 hours you are generating, 24 hours generating. So maximum you are utilizing with the hydro alone. Maximum you are say for example 18 hours you are utilizing with the hydro alone. Just 6 hours only you are utilizing with the your thermal. Then automatically the cost being involved will be reduced. So here also what we are doing is we are maximum you're utilizing the hydro. So if you say like a phj, j is nothing but the time period. Say for example j is equal to 1 to j maximum. So it is from 1 hour to maximum of 24 hours. So say for example here we are generating only with 18 hours, 1 hour to 18 hours. So the maximum so we need to generate the maximum power is being generated from the hydro only to meet out the demand. So if P Sj is maximum, then the cost is being increased. So that is what here it is. The hydro power plant can supply the load by itself for a limited period of time. That is limited period. What I said, some 18 hours. Say for example 18 hours. So take this as equation number 1. Okay, take this as equation number 1. That is PHJ maximum is greater than or equal to P low. Okay, say for example in this scenario, what they are trying to say is we are we are utilizing this hydro for maximum period of time. Say for example 24 hours. We are utilizing maximum 24 hours, or otherwise to the greater than the load for the load. Say for example load is 1000 megawatt, means we are generating the power for whole 24 hours. That maximum 1000 megawatt we are generating with the hydro alone, like that they are telling. So we are taking phj maximum is greater than or equal to p load of j. So where j is equal to 1 to j maximum. Take this as equation number 1. However, the energy available from the hydro plant is insufficient to meet out the load. You know, like so 24 hours you can also generate, but there is some based on the amount of water in the dam, there will be some forecasting. What they will do is they will be forecasting. So this is the amount of water, so this much tmcs of water is being available in the dam. So for this if we generate daily some 12 hours daily, 12 hours for 30 days, our the amount of water what we are having is we can utilize that amount of water for some 2 months or 3 months if we are daily using that for 12 hours, 12 hours, and that too we are generating only for some amount whatever the power is being generated is only some 200 megawatt or 500 megawatt. Like that if you plan, then we can easily meet up. But if you utilize the maximum, then only instead of 3 months it will come if you are generating that power for whole 24 hours in a day. Okay, 24 hours in a day for 1 month, so 24 into 30 days you are generating for 1 month. Then only the amount, the time limit might be decreasing. Instead of coming for three months, only it will come for only 1 month. Why? Because we are generating throughout the day, 24 hours in a day. So if you generate only 12 hours or only 10 hours, then you can optimize that thing also. So that's what here it is said. The energy available from the hydro plant is insufficient to meet up the demand. So definitely some backup is needed. Okay, so for base load, for peak load hours, some base load generating units are needed. Some steam is also needed. Okay, steam for peak hours, steam is also needed, and you can also utilize with the hydropower. Then this thing you could not satisfy. Okay, you only 1 month of period only you can maximum utilize. So here, if you take say like the energy available from the hydropower plant is insufficient to meet out the load. So PHJ of NJ is nothing but number of hours in a period of time. Number of hours. Say for example, particular period you have taken 2 days, 2 days schedule you have taken, or 1 day schedule you have taken. So what is the number of hours? It's 24 hours. With that 24 hours, 12 hours only being generated, or 18 hours only being generated, or 20 hours only being generated. Okay, so that is the NJ. That is the number of hours in a period J. So one period, if you take 1 day, if you take now, what is the number of hours? 24 hours. So particularly, how much hours we are generating from the hydro? Only 12 hours. So like that. So that is the NJ. Okay, so that is summation J is equal to 1 to J maximum. PHJ into NJ is less than or equal to load J into NJ. Okay, where J is equal to 1 to J maximum. Okay, so energy available from the hydro power plant alone is insufficient to meet out the demand, because load is very maximum. Okay, so you have to rely on some other thing also. Why? Because if you take all over the hydro power plant in our state or in our throughout the country, you could not able to manage, even though installed capacity might be there, but that much resources is not available. That much resource is not available, so insufficient. You have to rely on some other scheme or some other renewable energy resources, some other biogas or nuclear, to meet out the total demand. So that's what. So it is generally it is less than. It should not equal. Okay, it is not equal, but if you take for a particular demand, say for example 1000 megawatt, then sometimes it is possible, sometimes it might be equal to, but in the majority of the cases it is not. You should not meet out the demand only with the hydropower. So it is less than, it is, power generation from the hydro is less than or equal to P load. Okay, where NJ is number of hours in a period J. Next, NJ total period of time, that is J is equal to 1 to J maximum of NJ, that is equal to T maximum, that is total interval. Okay, say for example J is equal to 1 hour to 24 hours. So that is the total interval of the particular period. Okay, so we would like to use up the entire amount of energy from the hydropower plant in such a way that the cost of running the steam power plant is minimized. Okay, so that's what I said. If we are utilizing the whole hydropower plant for entire period of time, then the cost of the running cost of the steam power plant will be minimized. Say for example, in the 24 hours of a time, we are maximum utilizing. We are running maximum 20 hours, and rest 4 hours we are giving that schedule to the steam power plant now. Then the cost of the running time of the steam power plant is minimized. Automatically, it might be minimized. Then the steam power plant energy required. What is the steam power plant energy required? So the total load. How to meet out the total load? That is the power. Meet out the total load. So hydro plus steam is nothing but load. So whatever the power generated from the hydro plus whatever the power generated from the steam, that is equal to the load. Okay, so that's what here it is said. So steam alone, if you want to take steam alone, means steam is equal to load minus hydro. Or otherwise, if I want hydro alone means that is hydro alone is nothing but load minus steam is equal to hydro. That is steam plus hydro is equal to load. So whatever the power is being generated from the steam, that is nothing but load minus hydro. Okay, so because load is, say for example, load is 1000 megawatt. From hydro you are generating 600 megawatt. From steam, because you are less utilizing that. From steam you are generating for only 400 megawatt. But it is satisfying the demand. So hydro plus steam, that is 600 plus 400 is equal to load. What is the demand? Load is nothing but demand. So that is 1000. Okay, so that's what here it is said. So load minus hydro is equal to E. So E is nothing but that is energy. Energy is being generated from the hydro alone. So E is nothing but the power that is generated from the steam for a period of time. Say for example, E is nothing but here E is nothing but PSJ into NJ, where J is equal to J is equal to 1 to NS. NS is nothing but number of period of time, number of period that steam plant is running. Okay, whatever the period of time that steam plant is run. Say for example 4 hours or 6 hours, whatever the thing that is in the period of maximum schedule. The maximum schedule 24 hours. That is a number of periods the steam plant is run. Okay, how many periods that steam plant is run? That is nothing but NS. Okay, NS is nothing but that is so this equation you take it as equation number 4. This you take it as equation number 3. Okay, so load steam plus hydro is equal to load, or steam alone if you want to take out, because we want to minimize the running. We want to minimize the running cost of the steam, so that the that is our main objective. We want to run the steam power plant for a very minimum period of time, whereas for hydro you can run up to maximum. Okay, so this you can take as 3 and this is take it as 4, where NS is number of period that the steam plant is run. Okay, and if you take like this NJ, what is NJ? NJ is nothing but number of hours in a period J. Number of hours in a period J is less than or equal to T maximum. What is T maximum? That is T maximum is entire interval of time. So obviously, if it is less than if steam is if you want to minimize the steam cost, then NJ, number of operating hours of NJ, should be less than T maximum hours. Okay, so up to 24 hours is there. So if you run that steam power plant for only for 12 hours, sorry, 8 hours, 6 hours, then automatically the cost of the generation from the steam plant will be minimized. Okay, then what is the main objective function of this hydrothermal scheduling? What is the main objective function? We have to minimize the total cost. We have to minimize the total fuel cost from the steam power plant alone. Steam power plant alone. That is, minimize F of T is equal to summation J is equal to 1 to NS F of PSJ into NJ. Okay, so our ultimate objective function is to minimize the total fuel cost. Total fuel cost that is incurred in the steam power plant. Steam power plant for certain hours. Say for example 6 hours or 8 hours, like that. So we need to minimize the total fuel cost. Subject to, what is the constraint? Subject to this constraint. What is this constraint? Subject to PSJ into NJ minus E. Okay, if you minimize this thing, then automatically the cost will be reduced. So subject to summation I is equal to J is equal to 1 to NS into PSJ into NJ minus E is equal to 0. Okay, so this is the constraints. Okay, so next we are having objective function and as well as the constraints. So how to frame the Lagrange's function? So Lagrange's function is nothing but your objective function plus some constant into constraints. So what is the constant here? Here we are taking this alpha. So what is the objective function? Objective function is to minimize the total fuel cost. So here minimize the total fuel cost. Summation J is equal to 1 to NS f of psj into nj plus this constant, that is alpha into this E minus. Okay, so we are taking this energy generation from the power, that is energy generation from the E. E is nothing but energy, maximum energy generated from the steam power plant is greater. So obviously it might be greater. So E minus summation J is equal to 1 to N, Ns into Psj into Nj. Like that we are taking. Okay, and we need to solve this Lagrange's function. So we need to differentiate. We need to differentiate, and we need to equate it to 0. We need to because we need to find out the what is the change. What is the change? Small change with respect to power generation in the steam power. Okay. So if you want to we want to minimize the total. If you want to say, for example, in the same scenario, if it is maximum case, if you want to maximum, say for example, if you want to maximize the power generation from the hydro, then accordingly you need to take that hydro constraints, and you need to integrate for whatever the hours. Say for example, for hydro you are running for 0 to 18 hours. So for 18 hours, what is the maximum hours it is running? So you need to find out that particular thing. But here in this hydro scheduling problem, so what is our objective? To minimize this thing. So for minimizing, we need to differentiate with respect to what we are doing is we have to minimize this power generation from the steam generating unit. So what we are doing is we are minimizing the power generating from the steam generating unit and equating it to 0. So here we are differentiating. So while differentiating, we will get this. So that is df of psj divided by dpsj minus alpha. This term we are neglecting, so this term will become 1. So alpha into 0 minus 1, so 1. So alpha into minus 1 is minus alpha, so here it is minus alpha, it will come, so equal to 0, where j is equal to 1 to ns. Okay, so this term along that is df of psj divided by dpsj is equal to alpha. So okay, if you further simplification, that is equal to alpha for j is equal to 1 to ns. So this means that steam power plant should run at a constant incremental cost for a period of time it is on. Let let this optimum value of steam generated power be ps star. So what we are taking is we are taking this optimum value of power generated from steam power generating unit as PS star. Why? Because as I previously said, we have to less generate this. We have to less generate the power generation from the steam generating unit. So that is we have to optimum utilize. So what we are doing is what we are taking is we are taking this notation, that is optimum value of the power that is being generated from steam as PS star. We are taking this as PS star, which is same for all the time intervals until the steam unit is on. Until this steam unit is on. So if you see this figure, you can better understand. If you see this figure, you can better understand. That is, this is the total schedule. This is the total schedule that is for maximum period of time. Say, for example, it is for T maximum hours. T maximum hours for 24 hours of time. 24 hours of time. You, if you see this shade, okay, this shade is fully of hydro. So hydro, you have to maximum utilize hydro, and you have to less utilize the steam. You have to less utilize the steam. So what we are taking is we are taking this as P star. Whatever the power that is being generated from the steam generating unit, that is being given in this shape. Okay, so that we are taking as PS star. Okay, so that is the optimum value of the power that is being generated from the steam power unit. So from this figure itself, you can easily understand how optimally we are utilizing the steam power plant rather than this hydro power plant. Whereas the hydro power plant, we are maximum, that is maximum we are generating for maximum T max hours. But for steam power, only we are generating for TS hours. That is, as I said, like 6 hours or 8 hours, like a very minimum amount only we are utilizing the steam. And also power generated, that is power is being generated, is also very, very less, that is PS star, that is optimum value. So to meet out the total demand. So this is the, say for example, this is the PL, total demand PL, or total load PL. So in this schedule, we are less utilizing this power generation from the steam power. So this is the resulting optimal hydrothermal schedule. This is the so this axis we are taking as time axis. This axis we are taking it as power generation axis. Power generation axis. So in this figure, it is clear that we are less utilizing the power generated from the steam generating unit, and also for less time also. Less time also. Okay. So that's what here it is said. Okay, so that is given in the figure. So the total cost over the period of interval, total cost. What is the total cost with combining this optimal power schedule? So FT, that is total fuel cost. FT is equal to summation J is equal to 1 to NS F of PS star into NS NJ. PS star into NJ. Where PS star is nothing but optimum value of steam generation. Okay, so that is nothing but if you take this F of PS star outside, then this summation J is equal to 1 to N NSJ, sorry, NS into NJ. Okay, so this value you can take it as this value already we have seen, that is NJ is nothing but TS. Okay, so total number of timers, that is NJ is nothing but total runtime for the steam plant, that is nothing but TS. So for instead of this term, we can directly take this as TS. Okay, instead of this term, we can directly take this TS. Take this as equation number 9. Next, let the steam power cost, let the steam power plant cost function is being expressed. This we have seen, that is F of PS is equal to A plus B into PS plus C into PS square. Okay, so here instead of this, but previously we have seen like A PS square plus B PS plus C. Like that also you can take, and this also you can take. The constant only it is varying. So instead of that, you can take it as PS square plus PS plus C also you can take. Nothing wrong in that. Okay, because all from the previous classes we have seen like that only. We can take nothing wrong if you take like this also, because only constant only varied. So no problem if you take like this also, no problem. If you take if you write the notation like that also, that is nothing there, because A, B and C are the fuel cost coefficients. Fuel cost coefficient. So let FT is nothing but total fuel cost. Total fuel cost, that is A plus B into PS star plus C into PS star square, the whole into TS. The whole into TS. TS is nothing but the total run time for the steam plant. Total run time for the steam plant. This PS star already you know. Okay, and here you have to note that summation J is equal to 1 to N 1 to NS PSJ into NJ is nothing but summation J is equal to 1 to N NS into PS star. PS star is the optimum power generated into NS. Okay, so into NS. So this term you already know. Summation J is equal to 1 to NS into NJ is nothing but NJ is nothing but TS. So instead of this term, we can take it as TS. So PS star into TS. So that is nothing but E, capital E. Capital E, what is capital E? That is capital E is nothing but power that is being generated from the steam generating unit for that particular period, particular runtime, particular period of time. Okay, so that is you take this as equation number 10, 11 and 12. Okay, so equation number if you take, it is easy for to substitute and understand. Okay, so always you go with some equation numbers. Next, so with this, how to find out TS? TS is nothing but total runtime for the steam power plant. So how to find out TS? So Ts is nothing but E divided by Ps star. Ts is nothing but E divided by Ps star. Take this as equation number 30. So if you take like total fuel cost, what is the total fuel cost? A plus B Ps star plus C into Ps star squared into E divided by Ps star. Okay, so if you substitute, so here total fuel cost Ft is equal to A plus from equation number 11. A plus Ps squared plus C into Ps star squared into Ts. So Ts we already calculated. So just like that, we are substituting from the equation 11. From equation 11, so substitute equation 13 in equation 11. Substitute equation 13 in, then equation 14 will come. So take this as equation 14. That is Ft is nothing but this into this. Okay, so now we can establish the value of Ps star by minimizing the Ps. Sorry, by minimizing the total fuel cost Ft. Okay, so here DFT divided by dpt. So what we are doing is we are differentiating this total fuel cost with respect to Ps star, star and equating it to 0. So while differentiating, you will get like this: minus AE divided by Ps star squared plus CE, C into E. Okay, similarly you need to differentiate. I think if you differentiate this, okay, this will come like this. The equation will come like this. Later you can differentiate and equating it to 0. Okay, so you'll get the equation like this. So but the main thing is that we need to find out the optimum value of the power generated from the steam generating unit. What is the optimum value? That is nothing but Ps star. So Ps star, further simplification. So Ps star is nothing but, so if you take this term outside, so it will come minus CE. And if you take this term, that Ps star outside, further simplification, you will get root of A divided by C. Okay, you take this as equation number 15 and you take this as Ps star as equation number 60. So which means that the unit should be operated at its maximum efficiency. Okay, so if this condition satisfies, that is Ps star root of A divided by C, if this condition satisfied, in this condition, this unit is operated in the maximum efficiency because this is the optimum value. Okay, so maximum efficiency point long enough to supply the total energy E, capital E. Okay, so this you know, f of Ps star is nothing but A plus P Bs plus C into Ps square. That is nothing but Fc, that is fuel cost function, into H, heat rate characteristics. H of Ps. H of Ps nothing but heat rate heat rate of this steam power generating units or hydropower generating unit. So where Fc is nothing but fuel cost. Okay, you know very well know the heat rate into fuel cost is nothing but fuel cost. Characteristics. Sorry, fuel cost. Okay, so this is nothing but fuel cost. So this is nothing but here f of Ps star is nothing but here fuel cost, total fuel cost of the steam power generation. So that you already know. So with the further simplification, that is Hs of Ps divided by Ps. You take Ps outside divided by Ps. If you use further simplification, it will come like 1 divided by f of Fc into A divided by Ps plus B plus C into Ps. So heat rate, so ultimate aim, what is our ultimate aim? So heat rate should be minimum. It should be minimum. Heat rate should be minimized. So heat rate should be minimized means, so we need to differentiate this heat rate and equate it to 0. Okay, so what we are doing is we are differentiating. We are differentiating this heat rate characteristics, that is this equation, that is equation number 18, with respect to Ps. Okay, and equating it to 0. So further we are differentiating, we will get like minus A divided by Ps squared plus C. Okay, take this as equation number 19. So similarly, all you take the equation numbers. from 1 to 19. So this we are taking it as equation number 19, which gives the best efficiency. So further simplification, we want only PS or PS star. Okay, so which gives the maximum efficiency at PS star. So further simplification, PS star is nothing but root of A divided by C. Same answer only will come. Why? Because here also with the fuel cost also the same answer. PS star is nothing but root of A divided by C, and with the heat rate also the same answer will come, because heat rate, that is fuel cost, is nothing but that the fuel rate into that heat rate. Okay, so fuel rate is nothing but fuel cost into heat rate. So that also you'll be getting that same answer, that is PS star. So PS star is nothing but the optimum value of the power is being generated. Optimum value of the power is being generated from the steam power generating unit. So that is nothing but PS star. So that is PS star is nothing but root of A divided by C. So which gives the best efficiency. Okay, so best efficiency, PS star is nothing but root of A divided by C. So take this as equation number 20. So like this, you need to solve for the that is if optimal schedule is satisfied, then automatically the power generated from the hydro will be increased as per this diagram. Okay, if this is decreased, if PS star is decreased, the power generated from the hydro is being increased, then the total cost being incurred for the whole time, that is T maximum hours for 24, say for example 24 hours, will be reduced. Okay, so if you reduce this PS star, that is if you optimum utilize this PS star, automatically the total cost for the whole whole T max hours will be reduced.